So before we start the lab, we wanted to calculate a few things. First of all, the diameter of our pinhole and the focal length of our collimation lens. And these were based off of a couple things. First of all, our input beam waist and the focal length of the subjective lens. Numerical aperture also matters too. Now, we wanted to fully fill the shear plate entrance, but one thing was important. We wanted to make sure the shape factor of our lens, because it's plano-convex, would be -1 shape factor. And this reduces spherical aberrations, which will improve the results that we're getting on the shear plate while we're observing it. So with our known expansion ratio, which is based on our input beam waist, our known beam waist based on the input of our shear plate, and our focal length of the objective lens, we could find the focal length of our collimation lens, which is 300 millimeters. We could also find the pinhole diameter, which is based on the wavelength of our laser beam, 632 nanometers, the focal length of our objective, which was around 6 millimeters, and the beam waist of the input. And now we found the diameter would be roughly 25 microns. And we wanted to completely fill the shear plate entrance diameter because it increases shear plate sensitivity, which is important for this lab. What exactly does the shear plate tell us? Well, the shear plate tells us the shear distance, and now that is seen by this S parameter, which is the distance from the center of each interfering beam. It's also the distance between where the beams are interfering, the edge of it, and the edge of the circle of the beam. Now, this parameter for a non-wedged plate is consistent as long as our input beam angle is consistent. It's based on the refractive index and the thickness of the plate, and it doesn't change. But if you have a wedge, it is a function of the position on the wedge. Our parameter D is the fringe spacing. Our parameter alpha is our angular deviation off of this reference line in the middle here.
Now, to measure the shear distance of our shear plate, we defocus it slightly so that we're able to get these two spots for the beams. Then we use a vernier caliper to measure the distance between the two centers of the beams to get our shear distance.
So here we have an exaggerated diagram of what's really happening. We have a mirror and it's moved to two different positions, position 1 and position 2. Over here we can see that the angle at which the beam converges after hitting the mirror at both positions is the same. That means that our fringe spacing and orientation of the fringes, or orientation angle, stays constant.
Here's the results for the low power mirror. This equation here was used to calculate the radius. At position M1, we calculated the radius to be 19.54 meters, which makes the focal length 9.77 meters. Position M2, we have the radius at 19.85 meters, which makes the focal length 9.93 meters. It's a concave mirror, and the estimated percent error of the radius measurements were about 5%.
So in this part of the lab, we're testing the focal length of a low-powered lens depicted here. The input to the lens is the already collimated, already expanded beam from the previous part of the lab. The output goes through this simplified picture of the shear plate interferometer and up onto the viewing screen, and we get these interference fringes. Because it's a low-powered lens, it's only converging slightly. That means we can collect all of the same data that we collected for the low-powered mirror and use that to find the focal length of this low-powered lens.
Here are the results for the low-power lens. We used essentially the same methodology. For the radius, we got 60.61 meters, which made our focal length at about 121.21 meters, which makes it essentially a plane parallel plate. It's a positive lens, and the estimated percent error for the focal length was about 5%.
So for this part of the lab, we're testing the radius of curvature of a curved mirror. We have our input to this shear plate interferometer as our already collimated, already expanded beam from the previous sections in the lab. We have our shear plate interferometer with the plate oriented this way, and then we have a reference lens right here of known focal length. We set our mirror being tested at the focal length of this reference lens and adjust it slightly until we get our fringe pattern here parallel to the reference line. Then we shift our mirror downstream until the fringes again line up parallel to this reference line. The distance that we've shifted the mirror is the radius of curvature of that mirror. So the reason that this works is that at the first position, we're focusing this laser with this reference lens down to a very small point on this mirror. At that very small point on the mirror can be safely assumed to be planar, and that just bounces the laser back, recollimates it, and that's why we get the interference fringes parallel to that reference line. At the second position, the reason that they're parallel to that reference line is because we've shifted it so that the wavefront of the laser, the radius of that wavefront now matches the radius of curvature of this mirror. So it bounces it directly back along this beam path, focuses it to a point here, and then that acts as a point source, and then this lens recollimates it and sends it back up through.
These are our results from the high-powered mirror. Delta Z equals 200 millimeters, and so therefore R equals 20 centimeters.
That's fine.